Allow me to start this video with a question. Here we have a running 4-stroke engine. And let's imagine that combustion is occurring inside the combustion chamber, inside the cylinder, above the piston rings. The question is, what is the pressure below the piston rings inside the crankcase? Is it A, the same as ambient, i.e. atmospheric pressure, B, higher than atmospheric pressure, C, lower than atmospheric pressure, or D, all of the above? Time's up. The answer is D, all of the above. How can it be all of the above? It can be all of the above because pressure inside a crankcase fluctuates. It can be both higher and lower and the same as atmospheric pressure. And in this video, we're going to learn and explain why that is not really a good thing and why what we ideally want inside a crankcase is this: C, vacuum, lower than atmospheric pressure. So why does pressure inside a crankcase fluctuate? It fluctuates because, number one, engines have piston rings, and piston rings cannot create a perfect seal. And number two, engines have a PCV, or a positive crankcase ventilation system. So as combustion occurs inside a cylinder, there's always a little bit of blowby. In other words, tiny amounts of combustion gases will escape past the rings and go into the crankcase. As these gases accumulate inside a crankcase, they of course increase the pressure inside it. If we allow these gases to increase without control, then the pressure would increase without control and we would blow out seals and send dipsticks flying out of the engine. This is why we have a PCV. A PCV is a simple system that essentially consists of some hoses and a valve. The hoses are connected to the crankcase and the intake manifold, and the valve sits in between. The valve opens and closes depending on the pressure inside the intake manifold and allows excess pressure to escape from the crankcase and these gases to be recirculated back into the engine. So basically, when the PCV valve is open, the pressure is slightly below atmospheric, and when the PCV valve is closed, pressure is slightly above atmospheric. In reality, crankcase pressure constantly fluctuates as RPM and manifold pressure changes, but what's important to understand is that these fluctuations are absolutely minimal. And while this is technically the correct answer, crankcase pressure can typically only go something like 5 to 10 millibar above and below atmospheric. So technically, this D is the correct answer, but really you wouldn't be wrong even if you answered A, atmospheric pressure, because the fluctuations are absolutely minimal. But as we said, that's not ideal. What we ideally want is C, vacuum, and we want significant vacuum, something like half a bar of vacuum if possible. Of course, a conventional PCV system can never hope to achieve anything near that. The only thing that can achieve such high vacuum is a dry sump system. So why do we want vacuum inside a crankcase? Because vacuum in the crankcase means more power. If you observe an engine in operation, you will see that the volume of the crankcase is constantly changing. This is the volume of the crankcase when the piston is at top dead center. And here's the volume of the crankcase when the piston is at bottom dead center. As you can see, these volumes are very different. This tells us that when the piston goes from top to bottom dead center, it must work to push a large amount of gas through the PCV or crankcase breather. Of course, it's impossible to push a large amount of gas through a tiny hole rapidly, so the piston actually ends up wasting some of its energy on compressing the crankcase gases and increasing their pressure. This can be especially problematic on engines like 360-degree twins or boxer twins, where we have a massive change in crankcase volume because both pistons are at top and bottom dead center at the same time. But if we create vacuum inside a crankcase, then there's a lot less gases to compress and there's much less energy wasted. In fact, energy is gained because now the downward travel of the piston is made much easier. A vacuum means that there is much less resistance. This is why if you throw something in space, it will keep traveling at a constant speed forever. There's no gravity and there's no air resistance. Outer space is a perfect vacuum. And how does a dry sump system achieve vacuum in the crankcase? By sucking everything out. So instead of a traditional deep wet sump that stores all the engine oil, we are going to have a very shallow sump or oil pan. And then instead of an internal oil pump, we will have a belt-driven external oil pump hooked up to the crankshaft pulley. So the pump runs whenever the engine runs, and pump speed and pressure increases as engine RPM increases, just like a conventional oil pump. This external pump scavenges or sucks oil out at multiple spots in the shallow oil pan, and then sends that oil into an external oil reservoir. At the same time, it takes oil from that reservoir, pressurizes it, and feeds it back into the engine. These are called pump stages. The first one will almost always be pressurization, and the remaining ones will be scavenging or suction. The more stages we have, the higher the vacuum inside a crankcase we can create. Okay, but this looks like a lot of extra parts and hoses and complexity just to achieve crankcase vacuum. Is it even worth it? Yes, it is, because crankcase vacuum is just one of the many benefits that a dry sump system achieves. The next important benefit of a dry sump is that it makes the life of the crankshaft a lot easier. If you ever opened a car window on the highway and stuck your hand out, you have probably noticed how air resistance acts against your hand. Typical legal highway speeds are between 120 to 130 km per hour, but the crankshaft spins even faster. Depending on the RPM and the radius of the crankshaft, a point on the edge of the counterweight can reach speeds of 200 km per hour or even higher in some cases. So you can imagine the air resistance the crankshaft faces all the time. But the problem is made much worse by the fact that the crankshaft doesn't spin in an environment of only air. In a conventional wet sump system, the oil drains from the rotating assembly down into the sump through the force of gravity. As the oil falls down, it of course passes by the rapidly rotating crankshaft, which then acts like a blender and creates a chaotic tornado of air and oil. So the counterweight edges traveling at 200 km per hour have to push through this environment of air and oil droplets all the time. This, of course, is another power-reducing loss. This is why some people modify their crankshaft through what is known as knife edging. They cut the ends of the counterweights to hopefully make them more aerodynamic and reduce windage losses. And while this can help in some cases, it is ultimately a band-aid fix because it does not address the source of the problem. But a dry sump system does. In a dry sump system, the oil does not stream down from the rotating assembly via gravity. It is actively sucked out of the engine crankcase. In other words, it doesn't spend enough time, and it's not present in a sufficient quantity in order to be churned up into a froth by the crankshaft. And because we create a vacuum inside the crankcase, the crankshaft doesn't have to fight as much air resistance. But it's not just the crankshaft that benefits. The piston rings benefit as well, because a dry sump system improves ring sealing at high RPM when blow-by is highest. In a conventional engine, when the piston goes down, it briefly compresses the gases in the crankcase and increases pressure. This increased gas pressure pushes back against the piston rings, making sealing worse. But if we have a vacuum inside the crankcase, then there's nothing pushing back on the rings, and they are free to release all their tension on the cylinder, making ring seal better and improving compression and power and also reducing emissions. All of this means that at high RPM, a dry sump system can increase peak power output by 5 to 10%, depending on the size of the engine and how much vacuum is achieved in the crankcase. So if you have an engine making 500 horsepower, then you can increase peak power by anywhere from 25 to 50 horsepower. And this is made even more impressive when you consider that the dry sump system is essentially a parasitic loss. It is a belt-driven pump. A multi-stage setup is especially bad because it has multiple pumps on a single shaft driven by the engine. So for example, if you have a 7-stage dry sump system, then you have 7 pumps, 7 rotors on that shaft. But the parasitic loss from those 7 pumps is still less than the pumping and the windage losses inside the crankcase, which is why a noticeable net power gain is achieved. But this is still just the beginning of the benefits of a dry sump system. Something else that's very important that a dry sump system achieves is that it helps the engine run cooler.
This is a 2000 Yamaha TT600R and it has a super simple dry sump setup. Here's our engine and here is our external oil reservoir.
Oil is taken from the engine via this hose and deposited in the tank. The oil gets deaerated in the tank. In other words, the air and oil froth is separated into air and clean oil. The vapors return to the engine via this hose, and the filtered deaerated oil collects in the tank. From there, it goes through this hose at the bottom of the tank, back down into the engine, and then it's forced into lubrication passages by the oil pump.
So basically a dry sump system just like on any other vehicle. But the fact that here we have just one single stage pump, it means that this system is not capable of achieving significant vacuum in the crankcase, which means that here the goal isn't to increase power. Here the goal is to increase oil capacity. This is a 600cc engine, but it has 3 liters of oil capacity. Compared to my daily driven Kia, which has a 1.6 engine, but only 4 liters of oil. So a 166% larger engine only carries 33% more oil. An air-cooled off-road motorcycle like this one greatly benefits from increased oil capacity because it takes more energy, more heat to overheat a larger quantity of oil. Just like it takes more heat, more energy to boil 3 liters of water than just 1 liter of water. It's pretty obvious. A bike like this has been designed to traverse rough terrain at slow speeds, and it's air-cooled. That sounds like a recipe for overheating. So we get an external oil tank to carry more oil to prevent overheating. And I have recently confirmed this because I have traversed some pretty rough terrain on a very hot summer day, more than 30 degrees Celsius, and this bike never showed any signs of overheating. Another, just as illustrative but probably much more famous example of increased oil capacity through dry sumps are classic air-cooled Porsche 911s. They had air-cooled flat-six engines in the back, so not very good airflow by the anatomy of the vehicle. These engines had a displacement of anywhere between 2 to 3.8 liters, but they all had dry sumps and an oil capacity of anywhere between 9 to 14 liters of oil to ensure that the engine never overheats.
But wait, there's more. It's not just more power and temperature control. Another benefit is engine protection. The easiest way to kill an engine is to starve it of oil. And in a conventional wet sump system, an engine that is properly filled up to its specified oil capacity can still be starved of oil. Here's our engine, here's our sump, here's our oil pump pickup, and here's our oil. Now let's imagine our vehicle brakes very hard. When that happens, all our oil will be pushed to the front of the sump, and during those short moments, the oil pump will ingest air through the pickup tube, leading to temporary oil starvation and potential engine damage. Of course, the same thing can happen during hard cornering, when all the oil gets sloshed to the side, or during very hard acceleration if the vehicle is capable of it, when all the oil gets pushed to the back of the sump. Now, sump baffles, they can help with this, but they still do not address the source of the problem, and that is the fact that the oil pickup must be fully submerged in the oil at all times to guarantee oil delivery. A dry sump completely eliminates this problem because it eliminates the need for an oil pickup. Instead, oil supply is guaranteed at all times and in all conditions, regardless of the G-forces acting on the engine. A really good example of an application where dry sumps are absolutely critical is aerobatic airplanes. Upside-down flying, extreme climbs, Cuban-8s, and all kinds of rolls and loops would all easily kill any wet sump engine within seconds. This is why all aerobatic airplanes rely exclusively on dry sump lubrication systems. No, we are not done yet. There's more benefits. Something else a dry sump can do is increase your redline. A 4-stroke engine typically has a redline in the first place due to 3 reasons. Reason number 1 is usually valve fault. At a certain RPM, the valve springs can no longer guarantee that the valve closes fast enough, And so we have contact between the valve and the piston leading to engine damage. Reason number 2 is usually that a rotating assembly is not designed to sustain forces beyond a certain RPM. And reason number 3 is that your oil pressure starts falling off. Number 1 and number 2, we can solve those with hardware changes. We get stiffer valve springs and or maybe some other components in the valve train get upgraded. For the rotating assembly, we get stronger components, we balance them, and those delay catastrophic events further higher up in the rev range. Number 3 can only be resolved truly by a dry sump system. At a certain RPM, your crankshaft speed is so high that it churns the air and oil, it froths it up, it aerates the oil. In other words, it creates a perfect air and oil mix. They are perfectly mixed together. But the oil pump is not designed to work with an air and oil mix. It wants just oil. And that's because oil is not compressible. It's a fluid. But air is compressible. And so at high RPM, what the oil pump does is that it sort of partially compresses this air and oil mix instead of maintaining desired oil pressure. And so at high RPM, oil pressure starts falling off. And at high RPM, you definitely do not want your oil pressure to start falling off. Again, of course, a dry sump fully solves this because it sucks out all the air and oil and moves it to a separate tank. There, the oil gets de-aerated. It calms down, it cools down, and only then it gets sent back into the engine. Okay, just one more benefit, and then I'm going to stop. Lower center of gravity. Think about it. If we replace a tall, deep wet sump with a tiny little oil pan, then suddenly the engine becomes a lot less tall. And that means we can mount it lower in the vehicle, and the engine is very heavy, which leads to a lower center of gravity and better handling. So there you go. Many benefits. What are the drawbacks? None. The only thing I have, really, is added cost and complexity. And I often mention added cost and complexity as a drawback in my videos, but when it's the only drawback, it's kind of lame. It's like drinking water with your hand, okay, and then drinking water with a cup. And then you say for the cup, the drawback is added cost and complexity because, well, you have to buy a cup and you have to keep it somewhere when you're not using it. In that case, that's the drawback of every material object ever made. Stupid. I got one. It's not really a drawback, but it's all I have. Wrist pin lubrication. If your engine relies solely on the presence of the wet sump and the splashing around of the oil to lubricate the cylinder and mostly the wrist pin, then installing a dry sump will require you to somehow ensure proper wrist pin lubrication. In reality, you're going to be very hard-pressed to find an engine like that, especially nowadays, because most engines have dedicated wrist pin lubrication nowadays through one of the following means. They either are going to have a notch on the con rod, so oil can be spat up into the wrist pin. They're going to have squirters on the underside on the piston of the cylinder to lubricate the cylinder and the wrist pin and the underside of the piston. They're going to have maybe oil-drilled con rods, so oil goes from the big end right into the small end and lubricates the wrist pin as well. There's going to be something. But if there isn't and you put a dry sump on it, then you're going to have to install one of these to lubricate the wrist pin again. That's the best I can do for a drawback. It's not a real drawback. So, if there's no drawbacks, why aren't dry sumps in every engine? Well, the answer is pretty obvious. Added cost and complexity. You're going to find dry sumps in some vehicles from the factory. But it's going to be stuff like Ferraris, I believe the V10 BMW M5, yes, that has a dry sump. Some Audi R8s, I think. Some Z06 Corvettes. What else? Lexus LFA has a dry sump. Some Porsche GT3s, I believe. Basically, cars of that caliber. You're not going to find it in your daily driver, regular family hatchback thing because the benefits cannot be justified and these cars cannot reap most of the benefits because, for example, they simply can't achieve the G-forces that justify a dry sump. They aren't designed for prolonged high RPM operation, nor can they rev high enough to benefit as much from a dry sump. What else? The added 10% or 5% of power, again, doesn't justify the cost. You get it. Dry sumps are more common on motorcycles because, for example, in sport bikes, some of them rev very, very high, and there we have high blow-by, very high windage losses, so it's justified. We also have some extreme lean angles that can justify a dry sump, and we can also find them sometimes on dirt bikes where we have extreme, hill climbs, jumps, tough landings, wheelies, crazy loop, jumping maneuvers, you name it. That can sometimes also justify a dry sump. So there you have it, dry sumps. They are definitely awesome, but they are technically not dry because there's still oil in the sump. It just gets sucked out, right? Yeah, as always, thanks a lot for watching. I'll be seeing you soon with more fun and useful stuff on the D4A channel.